Okay, so before we start going over that worksheet and kind of covering, how to use the tables that you guys got yesterday and how the normal distribution curve um, works, I just want to take a second and go over some of the percentages that we learned yesterday, because some of the ones that were on the worksheet were a little off. Now, the reason that they're a little off is because some worksheets and some books, instead of using 68, 95, 99.7 rule, they use a little bit more of an accurate model that uses decimals. So it's not just 68, it's 68 with a decimal. And if that's the case, it just kind of throws off the percentages just a little bit. It doesn't matter which one you use for the AP test, but we're just going to redo ours just so it's a little bit more consistent with what we're showing you. Okay, so let's make sure this is written down. The mean, again, is right in the middle. And then as you go out, this would be 1 standard deviation, 2 standard deviations, and 3 standard deviations. On the left side, you have 1 standard deviation to the left, 2 standard deviations to the left, and 3 standard deviations to the left. Okay, so the way it works is from the first standard deviations, that is 68% of your data. Okay, the second standard deviations, when you break that up from here to here, that's going to be 95% of your data is going to be between those 2 standard deviations. And then for 3 standard deviations, all the way across, that's 99.7% of the data. So how does this break it up for each quadrant? Okay, so the first standard deviation to the mean, the whole distribution, that's 68%. So if we broke it up, that would be 34% and 34%. And these numbers are just good to know for later. So the distance from the first standard deviation to the second would be 13.5 or 13.5% on each side. Okay, so now the distance between the second and the third deviation, as that curve is getting smaller, we've got less and less of a percent there. Comes out to be about 2.35% per side. And then the whole from -3 standard deviations to +3 standard deviations, that comes out to be 99.7. So that's only 3/10 of data that's unaccounted for. So if we break up the 3/10 of data, that means not 1.5. Let me delete that for a second. That means that 0.15, come on, Pen, 0.15% of the data lies beyond the 3 deviations to the left, and 0.15% lies to the right of the third standard deviation. And then if you add them all together, that'll give you 100%. Okay, so now that we've gone over this, make sure you guys have these numbers, because it's just going to make your life a little bit easier as you type things out and as you work through your worksheets. So let's actually go back to yesterday's worksheet and that Major League Baseball problem, so we can build this normal curve and actually go through what it means and start to apply it. So going back to this example, said in 2009, the mean of 432 batting averages was 0.261, and the standard deviation of this was 0.34. Okay, we're going to create a normal curve because they want us to draw and interpret the normal curve. Okay, so every time we do this, with your x-axis, and then draw as close to the bell curve as you can. Okay, in the middle goes our mean, and our mean was 0.261. So 0.261. Okay, now as we go to the right, every time you come over, and we're going to have 3 standard deviations, you're adding that 0.034. So if you take 0.261 and you add 0.034, and you get the next batting average over, which is 0.295. Add it again. The next standard deviation, I'm going to put this on the bottom just to save some space, is 0.329. And then we'll do it one more. Comes out to be about 0.363. Okay. Now on the other side, because you're going to the left, you're taking away those standard deviations. So you're going to be subtracting. So start with 0.261 and subtract the 0.034. So we end up at 0.226. Okay, we do it again. We end up at 0.192. And then we could do it one more time. And we end up with 0.158. Okay, so what does this mean and how can we apply it? So what we can say is if we have the mean, and I'm going to highlight the mean again, the 0.261, that from here to here, from our first standard deviations, that's 68% of our data. Okay, so what we could say is that 68% of the 432 batting averages and then we can use those numbers at the bottom, were between, and then our first standard deviation was to the left was 226, and then the first standard deviation was 0.295. So 68% of those batters were between those batting averages. Okay, and then it kind of goes on from there. We can use this in so many different ways. So I could ask you, for example, what percent, and I'll write this down, what percent of the batting averages were above 0.192. Okay, so what you have to realize, and this is where the knowing all those percentages is actually going to really help out. Let me delete a couple of things so I can make some room. Okay, 0.192 is right here. That's our second standard deviation. That's 2 standard deviations to the left. So if I go back to my model earlier that we were talking about, which is right there, that's 2 standard deviations to the left. So pretty much, I want to know if the batting averages that were above it or to the right. So what I can do is I can just take all of these numbers, because those are all the percentages to the right, add them up, and that'll give me those percentages. Okay, so go ahead and do that. All right, and you come up with about 97.5% of the batting averages. So what they're pretty much telling you, if you're playing Major League Baseball, 97.5% of the players in baseball are batting above a 192. So set your scopes high, and maybe you can get there. And we can keep going with all these types of averages. We can ask, how many players, and that's a good question to ask. So let's do this. Let me delete some of these things to make some more room. Give you guys a couple more examples. Let me get rid of all this if I can. Okay. How about this? We'll say approximately how many players bat above 329. Okay, So if I'm looking at a problem like this, 329 lies right here. So if you notice, that's 2 standard deviations. 2 standard deviations away from the mean. Okay, so let's go back and look at our table again. 2 standard deviations for the mean were right here. So that means I have to add from 2 standard deviations, I got to add that number and that number. Okay, so 2.35 plus your 0.15% ends up to be about 2.5%. Okay, so 2.5% of the players batted above a 329. Now, we want to know how many players, not the percentage. So what I do is I take that 2.5% and I turn that into a decimal. So that would be 0.025. And then I multiply it by how many batting averages they took. So 432. Okay, when you multiply them together, and we're gonna round. We're gonna say approximately 11 batters. Okay, so batting above a 329 is actually pretty rare. Imagine how rare it would be to bat above a 363. Take a few seconds, try to figure it out, and see if you can come up with the answer. And if you notice, after giving it a few tries or trying to figure it out, there's only about, let's say, 0.15% of those batters will bat a 363. So as a decimal, that's 0.0015. And when you multiply that by 432, you get about 0.65. So what they're saying is less than one player. Okay, so maybe over the course of 2 years, one person might do it. So it's a very extremely rare circumstance. So anything that's happening on the very, very ends of the normal distribution, these are very, very rare circumstances. Okay, most of the time the data doesn't even, your tables that you're going to get won't even go that far. So just wanted to show you guys and start to work with these normal distribution curves before we move on to the next part. In the book, it actually talks about, because we're moving on now, what happens if it's rules for distributions that are not normal. Okay, there is a formula to kind of figure this out, to figure out those distributions and like how far away from the mean you are. And here this is. This is not on the AP test, so I'm not going to focus on it, but I wanted to bring it to your attention in case you wanted to take a look at it further. All right. So now we move on to the standard normal distribution, okay? Because it's being standardized, we're talking about z-scores, okay? And anytime you take distribution and you standardize it, what's going to happen is what we talked about earlier, is when you standardize your distribution, the mean always ends up being 0. And your standard deviation ends up being 1. So that would be 1 standard deviation, 2 and 3, -1, -2, -3. Okay? So when you standardize these scores, you get this nice normal curve with a mean of 0 and standard deviations of 1. It's just a very easy way of counting. So once you standardize these scores, you can, it's so normal and these things happen so frequently that you can actually, they actually created a table for it. And I'm going to show you guys how to use that table that I passed out yesterday. So take out table A, and we're going to take a look at how to actually use these. Okay, the proportions, and let me bring up the table so you guys can see it. Okay, the proportions are happening inside the table. So the proportions are what you're actually finding inside. But the z-scores, okay, the numbers for the z's, the standard deviations, are on the outsides. Now, if you notice, when you look at these, the vertical ones, these z-scores, they all end up at the tenth spot. And then on the side, these z-scores go to the hundredths. Okay? So just so I can show you how to read this, if you're finding a z-score of, let's say, 0.86, okay? You're first going to look at the z-score. Come on down. Let me erase this here. You're going to find the 0.8 column. Okay, there's the 0.8. There's your hundredths, or there's your tenths. So that's the 0.8 part. And then the hundredths is 6. So you're going to trace these down until you see out where they match. So a z-score of 0.86 ends up at 0.8051. Now, these numbers, like I said inside, are called proportion. Think of them as a percent. So if I had to round, this would be the 81st percentile. Okay, the 0.86, that's a z-score. So that's talking about how many standard deviations it is away from the mean. Or in this case, how many standard deviations away from 0 we are. So I just wanted to show you guys how that actually worked. Now let's actually go through and apply some of these. Okay, so first one says find the proportion, so we're trying to find the inside part, of the observations that are less than 0.65. Okay, so a big hint, draw out your standardized table, your normal table, every single time you do that. Okay, so here's going to be 0, right? That's the mean. And then here's the standard deviation. So 0.65 would be somewhere around here. And I want to find everything less than that. So I want to find everything to the left. So I'm looking for this shaded region. Okay? So 0.65 is our key. So let's go to our z-score table. That's the wrong one. Okay. Okay, I'm going to write this over here so we have it. 0.65. Okay, so my 0.6 column or row is right here. So there's the 0.6. And then the 500ths, we go to 500ths, we scale down, and then we get our magical number, 0.7422. So the answer to this would be 0.7422. Okay? Now, if you want to see this in percents, they ask for proportion, so we're going to leave it as a decimal. But if you turn that into a percentile, it would be about the 74th percentile. Okay? All right. Number 2. Find the proportions of the observation greater than 0.72. Okay, so again, I'm going to draw this out. Here's my normal curve. So here's 0, and here's 1. So 0.72 would be about here. Now I want to find everything that's greater than 0.72. So greater is to the right. Okay, now, anytime if you remember when we did percentiles, I said percentiles are anything that is less than the observation. So this, when you're finding percentiles and you're using z-scores, you're finding the area to the left. So if I want to find an area greater than 0.72, once I find that proportion, I'm going to have to do something to switch it around. So let's just identify the z-score of 0.72 first. Okay, go back to your table. Let me get rid of this. Okay, so 0.72. So let's find it. So 7 is my 10th spot, so that's here. 2 is my 100th spot, which is here. And they cross right here. Okay, so that's 0.7642. Okay, this is the proportion or the area on the left side. So that's here, 0.7642. Now, I didn't want everything to the left of it. I wanted to find everything to the right. So in order to find everything to the right, remember that the area under the curve adds up to 1. So all you have to do is do 1 minus that 0.7642, and you'll end up getting your answer. And it comes out to be approximately 0.2358. Okay, so mathematically, what this means is 76% of the data is to the left of 0.72, and about 23.58% of the data is to the right of that number as well. It will always add up to 100%. Okay? All right, number 3. Find the proportion of the observations that are between 0.32 and 0.49. Okay, so now we're trying to find in between these values. Okay, let's do it again. So here's our normal curve. Okay, right in the middle is 0, and then here's 1. So when we're looking at this, 0.32 is going to be about right here, and 0.49 is going to be about right here. And we want to find the percent that's in between those 2 points. So we're looking for that area right there. Okay, so again, we got to use these z-scores. So I've got 2 z-scores to find. I've got 0.32, and then I have a z-score of 0.49. Okay, so when I look these up, we're going to go a little bit quicker here. 0.32 ends up being right here, and 0.49 ends up being right here. Those are our 2 proportions. Okay, so at 0.49, I've got about 68.79% of the data to the left. And then at 0.32, I've got about 62.55% of the data to the left. So if I want to find the data between these, all I have to do is take these 2 numbers and subtract them. When I subtract them, that gives me 4, 2, 6, 0. Okay, so here's my proportion, there's my answer, and then to rationalize this, they're saying about 6.24% of the data falls in between these 2 values of these 2 z-scores. Okay. When I get back on Friday, I'm going to show you guys how to use the calculators to do this instead. So let's wait on number 4 and we will get back to it. Okay. Number 5 talks about finding the 80th percentile. Now remember, the percentiles are just like the proportions. They're located on the inside part of this chart. So this is almost like a working backwards problem. Okay, so I'm looking for the 80th percentile. So let's go to our chart. Now I'm looking for as close to 80%, or 80% as I can. So if I'm looking here at 0.7995, and then here would be 0.8023. Which one's closer? Okay, I'm going to use this one. Okay, because it's closer to 80%. So all I have to do is track that over to find the tenths, so 0.8, and track that up to find the hundredths, 0.04. So my answer for this one is 0.84. So at 0.84 standard distributions, you're going to end up giving the 80th percentile. So to make, again, we're trying to make sense out of all of this. What does it actually mean? So it's right there is my mean at 0, and there's my first standard deviation. 0.84 would be about right here. So at this point, this standard deviation, that's where about 80% of the data is less than that. Okay? All right. So far, so good. Let's keep on moving up. Okay, so what we can do in problems like, and let me kind of scroll back up to the Major League Baseball problem. If you look at problems in Major League Baseball, the mean wasn't at 0, and my standard deviations were not 1. So because this mean was a different number, it wasn't 0, we can't use the chart for it. But the way that we can end up using the chart for a problem like this is to standardize the data. Okay, so to standardize the data means we have to actually find the z-score. So let's actually take a look at at the Tiger Woods problem here, and then see if we can start to standardize the data so we can use the table to answer this. Now, in order to standardize the data, we're finding the z-score. The formula for that would be your observation minus the mean over the standard deviation. Okay, so let's take a look at this. We'll work through this problem together and see how it works out. On the driving range, Tiger Woods practices his swing with a particular club by hitting many, many balls. When Tiger Woods hits his driver, the distance the ball travels follows a normal distribution with a mean of 304 yards and a standard deviation of 8 yards. Okay. What percent of Tiger's drives are at least 290 yards? Okay, so best thing to do is to draw a picture for this. So we always want to make our curve. Here's our curve. Our mean goes in the middle, so 304 yards. And then 290, that's the key that we're looking at. So that's to the left. So let's count our standard deviations to the left. Okay? Now each time I go over one standard deviation, I'm going over 8 yards. So if I'm starting at 304, if I take away 8 yards from there, I'm at 296. If I take away 8 more yards from that spot, this point gives me 288 yards. So if you notice, 290 yards is not at a specific standard deviation. It's somewhere in between these values. So because it's not in a specific spot, I can't use this chart that we figured out earlier, because this chart's really only good for knowing where we're at each standard deviation. Okay, so how do we do this? We start by standardizing the score. We got to find the z-score. So in this situation, the z-score, our observation was 290 minus our mean, which is 304, divided by the standard deviation, 8. So 290 minus 304 divided by 8 ends up being negative 1.75. Okay. Now that we've standardized it, now that we have a z-score for it, now we can go back and use our table. So let's go to the table. It's going to be the negative, so you got to make sure that you're on the right side. We have to make sure that we use the z-scores that show these negatives. Okay? So I'm at a z-score of negative 1.75. So I'm going to scroll down. So here's the negative 1.7 row. And then the 500th column is right here. And they are going to intersect at 0.0401. Okay, now, as a percentile, that's about the 4th percentile. Okay, so that's only this information right here on the left-hand side. So they're saying 4% of his drives go less than 290 yards. But that's not what they're asking for in this problem. They want to know how many of his drives travel at least 290 yards. So I want to know how many are happening on the right side of this. So again, how would you find this value? If the 4th percentile, that's what's happening to the left, then the 96th percentile, or 96% of the drives are going at least 290 yards, 290 or better. Alright, so let's go a little faster through this one. It says, what percent of Tiger's drives happen between 305 and 325 yards? Okay, so we'll go quicker. We won't make the table this one, or the picture. We got to find the z-scores for both of them. So, for the first one would be the observation minus the mean 304 divided by standard deviation, which is 8. And the second z-score would be 325 minus 304 divided by 8. Let's get those z-scores. Okay, so we have a z-score at 305 yards came out to be 0.125, and the z-score for 325 was 2.625. Okay, now our z-scores only go to the nearest hundredth. So for this one, we're going to round at 0.13, and this z-score is going to be 2.63. Okay, let's go to our table and figure these out. So 0.13 would be 0.1 and 3 right there. So there's my proportion here. And 2.63, so we go to 2.6, and then scroll over till we hit 3. Is at that spot. So these are our two magic numbers. Okay, so to finish these questions out, if I'm finding the proportion between them, or the percent between them, I have to subtract them. 0.9957 minus 0.5517. So that's 0, 4, 4, and 4. So it's about 44.4%. So about 44% of his shots will inevitably be between 305 and 325 yards. Okay. All right. Last problem. High levels of cholesterol in the blood increase the risk of heart disease. For 14-year-old boys, the distribution of blood cholesterol is approximately normal, with a mean of 170 milligrams of cholesterol per deciliter of blood and a standard deviation of 30 milligrams of cholesterol. What is the first quartile of the distribution of blood cholesterol? Okay, so the first quartile represents the first 25%. Okay, so because it's the first 25%, this is a percentage or a proportion, so we can actually use our chart to find the z-score for this. Okay, so let's go back to the chart, and remember all of our, here, let me get rid of these numbers again, that was shading. So the 25%, all the percentages are located on the inside here. So if you notice, even at a z-score of 0.00, my percentage is at 0.500. That's 50%. So I don't even see, that's the lowest percentage on this page. So that means that my z-score has to be negative. So let's turn over the page and let's look at the negative one. So on the negative side, let's find on the inside where I'm getting close to 25% as possible. So that would be 25% would be as close to 0.25 as possible. Okay, as I'm looking across, 0.25. Oh, I gotta get another chart. Okay, so I had to find another chart and actually had this online. So about 0.25 or 25%, this is as close as I can get to it. Okay, this is 0.2546, that's too big. This is 0.2483, and then, so this one's closest. So the tenths would be negative 0.6, and then if I scroll up, 7. Okay, so there's my value right there. So my z-score ends up being negative 0.67. Okay, so now I have all the information that I need to figure out what value or what number I'm looking for. So all I have to do is plug these into the formula to find the z-score. So the z-score was x minus the mean over the standard deviation. So if I have my z-score, it's negative 0.67 equals, x is what I'm looking for, the value, minus the mean, which is 170 milligrams, divided by the standard deviation, which is 30. So there's just some basic algebra to finish this problem out. Multiply both sides by 30. So these 30s will cross out. And when I multiply these values, I get negative 20.1 equals x minus 170. And then to get x by itself, you just add 170 to both sides. And you get out approximately 150 milligrams. So let's make sure we label it per deciliter of blood. So mg over dl. So what this means is that 25% of the blood cholesterol of the students is 150 micrograms per deciliter of blood. Okay, the rest of this worksheet, we'll talk about it on Friday. Thank you guys for listening to probably the longest video I've ever made. I'll see you guys tomorrow.